All right, starting a fresh chapter today. We were talking about alcohols last time in chapter 13. And here in chapter 14, we're going to be talking about ethers. Ethers are very similar to alcohols. We said an alcohol has some kind of carbon group. It could be an alkane, an alkene, an alkyne, bonded to an OH. And really, we should probably write that like this because we know the oxygen doesn't have a linear geometry, it has a bent geometry. And so an ether is like an alcohol, except we're replacing the hydrogen of the alcohol with another R group. The two R groups could be identical, they could be different R groups, but they have to be R groups for it to be considered an ether. So one common mistake that students sometimes make with ethers is it's not correct that any time a carbon is necessarily bonded on either side of this oxygen, that this will be an ether, because the R group that's attached has to be some type of carbon that is bonded to hydrogens and carbons. So if it is a carbon group, that carbon has to be bonded. It could be sp2, it could be sp3, whatever it is. It could be sp. It's got to be bonded to more carbons and or hydrogens. It can't be bonded to an oxygen in this way. That makes a different functional group. So if I have an oxygen bonded to a carbon on both sides, but one of those carbons is part of a CO double bond, then this particular functional group is called an ester. So ether, ester, they kind of sound similar. Maybe it's difficult to always tell them apart, but there is an important distinction because ethers have a variety of reactions they'll undergo and properties that they have, and esters have a whole different set of reactions that they'll undergo, right? Because with the CO double bond here, it's a nice electrophilic site, creates a large partial positive, a nucleophile could come in, like maybe a Grignard reagent. It could come in there and push these electrons up, and then they'd swing back down, as we saw with an ester, and push out this leaving group. Can't really do the same thing with an ether. Looking at a specific example of an ether, if I try to treat an ether with a Grignard reagent, it won't react in the same way. And really, unless there's some other reactive site on the structure, it won't react at all, because for this carbon to take these electrons away from the magnesium and attack, it might be able to attack this carbon, or maybe this carbon, but to push an oxygen out with a negative charge is pretty unstable, and these carbon-oxygen single bonds are relatively stable, and so we really wouldn't see that occurring. And so we want to make sure you understand the difference between an ether and an ester, and how ethers are a lot less reactive toward nucleophiles specifically. And so there are tons of different ethers that occur in natural products and synthetic pharmaceuticals, and this is just three specific examples just to give you a sense for, you could have an ether functional group and a phenol functional group. You could have an ether functional group and an alcohol or an amine. So there's lots of different complicated molecules that have lots of different functional groups, but the ether functional group specifically is carbon, bonded oxygen, bonded to carbon. As long as those carbons only have carbons and hydrogens attached directly to them, then that definitely constitutes an ether functional group. So every time we talk about a new functional group in detail, we always talk about how to name that functional group. And there's two different ways to name ethers. There's the common naming system, which normally we don't learn because there's only a few common named compounds that are usually named based on their common naming system. Most of the time we use the IUPAC system. But ethers is kind of an exception to that. There are a ton of ethers that are much more frequently called by their common name than by the IUPAC name. So if you're going to name an ether by the common name, we want to learn this system. The parent name is just ether. In this case, the parent is just a single atom, the oxygen atom. And so then you have to name the R groups that are bonded to it as substituents. This is a 2-carbon group, so it's ethyl, 1-carbon group, methyl. Put those alphabetically. E comes before M, and you get ethyl methyl ether. In this case, we've seen this molecule a lot in lab. We use it a lot for separatory funnel liquid-liquid extractions. Terbutyl methyl ether. Right? So the ether means the oxygen. On one side there's a terbutyl group, and on the other side there's a methyl group. And so the B comes before the M alphabetically, so it's terbutyl methyl ether. Or sometimes we abbreviate it that way, which is also fine. So simple ethers that have easily named substituents are you'll almost always find them named based on this system. So you want to be at least familiar enough with that, so when you see those names, you'll know what the structure of the molecule looks like. If you have a more complicated structure, you might have to name the oxygen and one of the smaller R groups as a substituent. And the other R group, assuming it has more carbons than this one, would be the parent chain. So here's an example there. So if I have 1, 2, 3, 4, 5 carbons here, that makes pentane. And then on carbon 1 of the pentane, there's an ethyl group, but the oxygen there, instead of making that ethyl, it makes it ethoxy. Right? So anytime you have an oxygen bonded to some R group, that's an alkoxy group. And specifically, if it's 2-carbon R group, it's an F-oxy pentane. So here I'm naming one of my carbon groups as the parent chain, and this is the standard IUPAC system. And I'm naming the oxygen and the other R group on the oxygen as a substituent. This could also be called by the common naming system, which would just mean that the oxygen in that naming system is the parent, and we have to name both the ethyl and the pentyl as substituents. So it'll be ethyl, pentyl, ether. So ethoxypentane and ethyl pentyl ether are the same thing. And it would really just depend on which naming system you prefer. So unless I specify, you could name it with either system. If I specifically ask for the IUPAC system, this would be the name. If I specifically ask for a common name for an ether, you would name the two substituents, put YL suffixes on them because they're treated as substituents, and then the ether oxygen specifically would be the parent. All right, so let's look at a couple examples. So here I've got my oxygen as my ether. So in this case, the common naming system is going to be tricky because I could think of the oxygen as the parent and just call that an ether. And on one side it's easy, I've got an ethyl group, but on the other side I'd have to name this whole thing as a substituent, which I could do. But in that case, it's probably a little more effort to try to name that as a substituent than to try to name it as the parent chain. So instead of doing the common naming here, I'm going to use the IUPAC system, which means I find my longest chain of carbons, prioritize the carbon that's directly bonded to the oxygen if possible. So that would be 1, 2. I want to make sure that my longest chain includes my alkenes, just like we did before we talked about naming alkenes. 3, 4. So that would be my parent. And so the parent chain would be bute. It would be butane because there's an alkene, it would be butene. And I need to name or number where that double bond is. It's between 2 and 3. So I number that starts on carbon 2. So I can call that butene as the parent, or 2-butene as the parent. And so then I'd name my substituents. I have a substituent here, that's a methyl. I have here a chloro. and here, including the oxygen, because I haven't included any of this in my parent name. That whole thing is a substituent, so it's a 2-carbon group, so it would normally be ethyl, but the oxygen there makes it an ethoxy. And that's on carbon 1. The methyl's on carbon 2, and the chloro's on carbon 3. So then I would want to put that name together alphabetically. So I'd have the chloro first, then the ethoxy, then the methyl. Put that in front of the parent name, choose either of those two parent names. Then I have to look for stereochemistry. Are there any chiral centers that need an RRS configuration? No. Are there any double bonds that need an E or Z configuration? Yes. So I need an E or Z out here. Or I could put cis or trans. In this case, it would be trans because I have two identical groups, two methyl groups here on opposite sides of the double bond. So I could write trans there. Or I could look at whether it's an E or Z configuration, because not all alkenes that have a stereochemical configuration that's specific will have an E or Z configuration. To answer Jose's question, not necessarily, but the oxygen here will take priority over most other substituents. So there are a couple substituents that might take priority over that, but for now we haven't talked about any of them. So if possible, you want to give the oxygen the lowest number. And so I would number the parent chain starting from this side versus the other side. So in general, anytime we're numbering the parent chain, we want to give all the substituents the lowest numbers possible. But when certain substituents are given a priority, we want to focus more on them and make sure that substituent has the lowest number possible when numbering the parent chain. So if I'm looking at whether this pi bond is E or Z, I prioritize the two groups on this carbon, prioritize the two groups on this carbon, and when the top priority groups are on opposite sides of the pi bond, that'll be E. Any questions about that one? All right, so we made sure the oxygen had priority over the chlorine there. The way they determine which substituents have priority over others when it comes to prioritizing the numbering of the parent chain is not really very easy to remember. It doesn't really necessarily make sense all the time. But we want to remember that halogens are not very high in priority, and neither are alkyl groups. So an OH or an OR is a high priority group, and after that, the alkene or alkyne number would be a main priority to try to focus on as well. All right, so let's look at this one here. If you're given the name, you should be able to draw the structure by focusing first on the end of the name, which tells you what the parent molecule is and what that should look like. So I've got cyclohex. So I want to draw 6 carbons in a chain because it's or in a ring because it's cyclohexene. So I've got a double bond there somewhere, and I've got an OH on. So the cyclohexene the all suffix means I have an OH on carbon 3. So if I number this 1, 2, 3, I could put an OH on carbon 3. And where's the alkene? Well, it doesn't really have a number. So I have to assume that it starts on carbon 1 and bridges to carbon 2. And then I have a methoxy on carbon 1. So methoxy is 1 carbon. And the oxy implies there's an oxygen there. So I have an oxygen to a 1 carbon R group, a meth oxygen or methoxy group. And that's on carbon 1. And then my name tells me that there's an R configuration. So if I only have one R or S in the name, I probably, or should at least only have one chiral center, and so that's this center here. So I need a solid or dashed wedge here to correctly indicate the configuration at that center. So let's just try it with a solid wedge. If I put my OH on a solid wedge and then prioritize the groups, it would go counterclockwise, which would make it S. So that's not right. Right? It's supposed to be R. So I know I need to do the opposite of that. It should be a dashed wedge. That way, when I prioritize 1, 2, 3 and go counterclockwise, with the fourth priority group pointing away, pointing out at me, a counterclockwise is actually R, which makes that correct. All right, so here was the 2 quiz questions about naming. So if we want to name this one, our parent chain, we could try to name this and then name this and call it terbutyl whatever ether, but that would be maybe a little challenging to name. So let's make this our parent chain and name the alkoxy group as a substituent. So if this is my parent chain, it's a cyclo because it's a ring. There are 5 carbons of the ring, so it's a pent. And there's an OH on it, so it's cyclopentanol. The OH on the parent chain, included in the parent chain, means all I have to do is change the suffix to OL and then give that a number so I know which carbon that OH group is connected to. In this particular case, the alcohol and the ether are very similar, and I know that there is a difference in how to prioritize them, but that level of detail I'm not going to hold you responsible for. So if you wanted to number this chain 1, 2, 3, 4, 5, that will be fine. If you wanted to number it 1, 2, 3, 4, 5, that's also okay with me. So let's just give the OR priority over OH and use the inside numbering here. That would put my OH on carbon 2. So I could put cyclopentan 2-ol or 2-cyclopentanol as my parent chain. And then on carbon 1, this is a tert-butyl group, so I would call that 1-tert-butoxy. There's a butyl group, so if the oxygen wasn't there and the carbon 5 were just connected to the tert-butyl group, it'd be tert-butyl. But I have tert-butoxy because there's an oxygen there creating that ether. So I can call that 1-tert-butoxy 2-cyclopentanol, or if you labeled it on your answer as 2-tert-butoxy 1-cyclopentanol, I would also give you credit for that because those two are very similar, and I don't necessarily expect you to remember how to prioritize them. All right, so here we have one we want to draw, and as I look at this name, I can see that it has the word ether at the end, and everything in front of that has a YL suffix. So that means in this name, this is the common naming system, not the IUPAC naming system. And my parent chain is also ether. So that would just be 1 oxygen. And Amy got me there. Thank you, Amy. We forgot to do the chiral centers here. So let me look at that. I'm going to redraw that structure so that we can focus on that detail. Yeah, we've got 2 chiral centers here, and very good point. Both of those need an R or S configuration. One is at carbon 1, and the other is at carbon 2. So if we look at this first name here, where this is carbon 1, and we wanted to determine its configuration, we would prioritize the groups attached there. So the oxygen would be priority 1. Oxygen has a higher atomic number than carbon or hydrogen. The priority 2 would be this carbon because it has got an oxygen attached versus the carbon that doesn't. This would be 3. Obviously, the hydrogen would be 4, so going 1, 2, 3 clockwise would make that an R. So this configuration here is an R. And when I numbered it this way, that was carbon 1. When I numbered it this way, it was carbon 2. So this carbon is R either way. It just depends on how you number your parent chain as to how you write that down. So let me just redraw it one more time, and we'll look at the other chiral center. So here we're looking at this chiral center here. Top priority is the carbon, or the oxygen has a higher atomic number than carbon. Second priority is the carbon that's bonded to an oxygen. Third priority is the other carbon. And the fourth priority obviously is the hydrogen. So when I go 1, 2, 3 counterclockwise, with the fourth priority group pointing away from me, counterclockwise is S. So that would be an S configuration. All right. Yeah, sometimes I have a tendency to go through these too quickly and not be careful. So definitely nice to have you there checking me over, making sure nothing falls through the cracks. So here we have the word ether, as we were saying. That means my parent chain is just the oxygen of the ether. And it's going to be bonded to two things: a phenyl, which looks like this, and on the other side, a 4-methyl cyclohexyl. So the main thing that's attached to the oxygen on the other side is the cyclohexyl. And if I think of this as a substituent and the oxygen as the parent, if my substituent has more substituents on it, I have to number carbon 1 as the carbon that's connected to the parent. Right? If I had some long parent chain, and I had something here that had a branch, if I were going to name this substituent, the whole substituent would be on carbon 4 of the parent chain, so it would be 4. But the chloro isn't on 4. The chloro is on carbon 1 of the substituent. So this 4 inside parentheses is like the 1 inside parentheses. It tells me which carbon of the substituent another group is attached to. And the first carbon of the substituent always has to be attached to the parent chain. So if the oxygen is the parent chain, this has to be my first carbon of the substituent. And then it doesn't matter which way I number around. But carbon 4 then would have a methyl group. And I can show that with a solid wedge or a dash wedge, since it's not a chiral center. If I can just flip the structure over or rotate it, it would be the same molecule either way. But that's on carbon 4 of the cyclohexyl substituent. So that would be the structure for that name. All right, so you should definitely practice some more naming. You never know if there will be a naming question on your weekly exams. Might also ask you some questions about the structure of ethers or properties. And we talked about alcohols recently, so we can compare ethers and alcohols together. So in an alcohol, the bond angle is a little smaller, right? If you remember what we said last semester, is these orbitals, the sp3 orbitals that hold the lone pairs, don't have any nuclei attached to them, which would have some amount of positive charge. So they're just sheer clouds of negative charge, and they repel the bonds. So they push the bond angle here a little bit less than it would otherwise be. Normally the bond angle between bonds on an sp3 hybridized carbon, and the bond angles between all 4 bonds, if it were like methane, they'd normally be 109.5 if they're all equal all the way around. But the cloud of electrons repels the bonded pairs better than the bonded pairs repel one another, so we get a slightly smaller angle here. The bigger the carbon group, though, the more steric hindrance it creates, the more repulsion that causes. So in this case, we see the opposite effect. We've got these big methyl groups instead of hydrogens, and their big electron clouds get a little too close together and repel. It's going to push them, they're going to be pushed away from one another. And so the angle expands to something more like 112. So I might ask you I wouldn't ask you to quote these specific numbers, but I might ask you to rank the bond angles or talk about what factors cause the bond angles to be larger or smaller, and that's going to be based on the steric hindrance and the repulsion of the groups that are attached versus the repulsion of the lone pairs. So these oxygen atoms are going to be sp3. Are there going to be any exceptions to that? Is it possible to have an ether where one of my lone pairs may be in an sp2 orbital and the other maybe in an unhybridized p orbital? The sp2, sp3, sp2, and sp all have two lobes, but one lobe is very small compared to the other, so we don't draw it. The p orbital has like two equally sized nodes. So why would an electron pair ever go into a p orbital that's more elongated and holds the electrons farther from the nucleus that they're attracted to versus a more compact sp2? Well, normally it wouldn't, right? That's why normally these oxygens are all sp3, because normally the oxygen needs to have 4 sp3 orbitals to hold both lone pairs and to overlap to form both of the sigma bonds to make the ether. So the only time that one of these lone pairs wouldn't be in an sp3 would be if the overlapping, or if the R group that's attached to the oxygen involved carbons with a p orbital. Right? So if this carbon is part of a double bond, so maybe we have a pi bond here, in that scenario, there could be some resonance. So one of the lone pairs will also exist in a p orbital, and it will rotate so that some side-by-side overlap can occur there. And then the other lone pair will be in a more compact sp2, which would help to stabilize it closer to the nucleus. And then there'd be another sigma bond there with whatever the other R group is. So as long as the R groups attached don't have p orbitals, then the oxygen's lone pairs will be in sp3 orbitals, because they're more compact than a p orbital, stabilizes the electrons closer to the nucleus. But if the oxygen is adjacent to another atom, doesn't have to be carbon, some other atom, well, I guess it would have to be carbon for it to be an ether. Some carbon with p orbitals, then the side-by-side overlap of the p orbitals would stabilize the electrons more in a p orbital than in a hybridized orbital. And so then you would get an sp2 hybridized oxygen. So one of the big things about ethers is they don't form hydrogen bonds in the same way that alcohols do. So we talked about alcohols in chapter 13. We said an OH group of an alcohol is a big electronegativity difference, creating large partial charges. And then when the hydrogen carrying a large partial positive on one molecule attracts to the lone pair carrying a large partial negative on a neighboring molecule, that attraction is a hydrogen bond. It's a pretty decently strong intermolecular force, and that means that it's difficult to separate these structures, right? So that's why we said alcohols have relatively high boiling points, because to turn a liquid where the structures are close together forming these attractions into a gas, you have to break these attractions and separate the molecules from one another. So what's the maximum number of hydrogen bonds an alcohol can have? Well, if I look at the alcohol structure, its hydrogen can have one, and its oxygen lone pairs can each have one, right? If a neighboring alcohol group with a large partial positive came over and aligned there, it could form a nice attraction, and likewise with a large partial positive here, it could form a nice attraction to that lone pair. So one single alcohol molecule could have up to 1, 2, 3 hydrogen bonds. What about an ether? Well, an ether doesn't have a hydrogen bonded to the oxygen. It just has the oxygen. So the oxygen is still a lot more electronegative than carbon that it'll be bonded to on either side. So it still has a large partial negative, and it still has 2 lone pairs. So it could form up to 2 hydrogen bonds. It can't form any hydrogen bonds with other ether molecules, though, because ether molecules don't have a large area of partial positive to bring in and attract to those lone pairs. So with no hydrogen atoms with a very large partial positive to form attractions there, it can't hydrogen bond with another identical molecule of an ether. It could hydrogen bond with an alcohol. So we see ethers and alcohols are often readily soluble because they can make some nice hydrogen bonds to one another. Up to 2. The maximum number of hydrogen bonds an ether can have is 2. Unless it's in a pure form. If it's pure, then the number is 0, as we said. The ether, if it's only surrounded by identical molecules of an ether, it can't hydrogen bond to other molecules because there's no hydrogen anywhere with a large partial positive. And so what that means is the boiling point of an ether is much lower than an alcohol. Would you expect them to be elevated similar to alcohols? No. Because the alcohols can hydrogen bond with one another, right? So if this is an ethyl group and this is an ethyl group, and I've got ethyl alcohol in its pure form, all the molecules look exactly the same. They can all hydrogen bond. It takes a pretty high temperature to separate them. But if they're all ethers, if I have diethyl ether, then I'll just draw the structure. The oxygen is pulling electrons away from these carbons, so they do have pretty decent partial positives, but then those carbons are bonded to hydrogens or other carbons, and those atoms on the surface maybe only have their electrons pulled away a little bit, and so they have very small partial positives right on the surface. So not much attraction between one ether's positive end and its large negative end. And so they just don't attract one another very well. They attract through some minor dipole because there's a positive end and a negative end. But the amount of positive that's exposed on the surface to physically attract to a negative of a neighboring molecule is actually pretty minimal. And so we see that when we look at the physical properties. If we compare propane versus dimethyl ether versus ethanol, which are very similar in mass, meaning they have basically the same number of electrons and the same ability to form London forces. And when the propane only has London forces, its attraction with another propane molecule is pretty minimal, and that's why it boils well below room temperature. Dimethyl ether is very similar. It does have a higher boiling point than the propane because, as we said, there is a dipole here, and so when one molecule attracts to another, they can form some degree of a dipole-dipole in addition to the London forces that would exist there. But that doesn't really make that much of a difference when you look at it makes a significant difference, but not a huge difference compared to the hydrogen bonding. So when a molecule can hydrogen bond, the degree to which large partial charges can be right next to one another and attract between one molecule and a neighboring molecule is much stronger. So it takes a much higher boiling point to separate those. So the trend one is a difference in the types of dipole-dipole attractions, London forces, and hydrogen bonds for this versus just dipole-dipole London forces for this versus just London forces. If you have a few different ethers, then all three of these can only do London and dipole-dipole, right? This one isn't even very polar. So why would its boiling point be so much higher? because it's a much larger cloud of electrons with a much larger surface area, and that allows for the temporary shifting of electrons that occurs randomly anywhere on the cloud to create larger quantities and more frequent quantities of random shifted electrons to create these tiny partial charges that can attract to a neighboring structure. And so that's just a general trend we're already familiar with, where the larger the electron cloud, the more surface area of the electron cloud, the more chance there is for temporary partial charges to form on a structure so it can attract to its neighbors, and so the higher boiling point required to separate it from its neighbors. All right, so one of our common uses for ethers in organic chemistry is the use of ethers as a solvent. And so there are really three advantages to ethers as solvents. And you're probably familiar with these somewhat from your experience in lab. So you may have used terp-butyl methyl ether as a solvent for your liquid-liquid extractions. In the Grignard reaction we did for lab 2, tetrahydrofuran was used as a solvent. That's an ether, tetrahydrofuran. So whether it's that or terp-butyl methyl ether, one of the advantages of those ethers is what we just talked about. They're relatively low boiling points. Why is that an advantage? Because then you can just evaporate it after you're done using it as a solvent. And you can dissolve whatever you want, transfer that into your reaction or from a separatory funnel into a beaker, and then just wait for that solvent to evaporate or evaporate off under vacuum. And since it evaporates at such a low boiling point, you don't need much energy or temperature to boil it off. And so you don't have to risk that energy or temperature causing unwanted side reactions. Another advantage is that they do have a dipole. So there is a dipole here, a negative end and a positive end, a negative end and a positive end. And so that helps the solvent during a reaction to stabilize any partial charges that might form during the transition state, right? We talked about this a lot. Last semester we said, if you've got some substitution reaction, maybe some unstable electrophile and nucleophile attacking, during the moment of the attack, as the electrons are in the process of breaking and forming, that's the transition state. As soon as that forms, you either get the products or maybe it reacts backwards. But when the transition state forms, like for example, maybe a leaving group is leaving a carbocation, as it's pulling the electrons away, it creates partial charges due to the electrons shifting. In that moment, it's really unstable because the electrons are not in an area of effective orbital overlap where they can be stabilized in a molecular orbital, effectively attracting to the nuclei. And it's also even more unstable because these partial charges are areas of charge imbalance that are a little bit unstable. So if the solvent can come in, and it's an ether or some other polar solvent, and bring in some opposite charge to form an attraction there, then that can stabilize the transition state. So it can happen more often and produce the products at a faster rate because not as much energy is needed in the collisions, and a greater percentage of the collisions that occur will have the energy necessary by stabilizing the transition state through solvation, forming some partial charge attractions with the solvent. The ether does its job of increasing the kinetics of the reaction. And the third advantage is the ethers are not protic. So sometimes you want a protic solvent, but sometimes you don't. And when you don't want a protic solvent, when you want a polar aprotic solvent that has a low boiling point, can be easily removed after the reaction, ether is usually a good bet. So what's reaction where we don't want our solvent to be protic? Well, anytime we use a strong base or a strong nucleophile, like for example a Grignard. So in a Grignard reaction, you normally think of the magnesium sharing electrons with the carbon. The carbon might have some stuff bonded to it, But we'll want the carbon to be the nucleophile, right? Because the carbon-magnesium electron pair that's shared, carbon almost exclusively holds them so that magnesium can make its noble gas configuration. And when it does so, it takes on a very large negative. So if my solvent is an ether, it won't react because it's aprotic. If I have a protic solvent like an alcohol or water, that's no good because the Grignard will just pick up that proton. So if we want the Grignard to attack a carbonyl or an epoxide or an alkyl halide in the reactions we've seen, we can't use a solvent that's protic, or the Grignard or other strong nucleophile base will just react with that solvent. When we want to react with something else, we need a solvent that's aprotic. Specifically, the Grignard reaction, the ether is almost always used as a solvent, specifically for the Grignard reaction because of its extra ability to form some nice ion dipole or dipole-dipole or nice charge attractions with the magnesium itself. So that helps to stabilize the magnesium without these electrons even more. It helps to keep everything dissolved in solution, and it helps to allow the carbon to pull the electrons away from the magnesium because the magnesium already has these other electrons kind of forming attractions to it, and that makes the carbon much more likely to use that pair of electrons as a nucleophile to attack and form a new bond with some electrophile. And in the Grignard reaction specifically, the fact that the ether solvent is aprotic, as we said in the last slide, is a key reason. Right? We can't have the Grignard picking up a proton if we expect it to attack an electrophile. All right, so one other type of ether that is really interesting to me and worth mentioning, has some value synthetically, are these so-called crown ethers. So here's an example where the name of the type of structure is based on its appearance. Right? So you imagine you got some person here and they're wearing a crown, right? So a crown ether would just be a situation where their crown had an oxygen at certain intervals. That would be a crown ether, right? So obviously you're not wearing these molecules on your head. It's just that you imagine a person's head in here and that kind of looks like a crown sitting on their head, right? So crown ethers always have two carbon chains between the two oxygens. Turns out, and we're going to talk about this later in the semester, if you put two oxygens on the same carbon, oops, I don't want to do that, it becomes pretty unstable because of entropy. One oxygen will tend to shift its electrons in and push the other oxygen out. And so that creates two molecules instead of one, which allows for more variety in entropy, and so that's generally favored by entropy. So if we put two carbon chains between the oxygens, we don't have that issue, right? Even if this oxygen tried to push electrons in, there's no leaving group on this carbon. There's only hydrogens and carbon, and none of those can attract electrons and pull them away. So we can't do that. So we don't have to worry about that. So instead, what we've created are these large rings with oxygens every third atom. We can make it a relatively small ring. We can expand the size by putting 5 oxygens instead of 4 or 6, and that determines the name. So these have cool names. The total number of atoms in the ring, followed by the word crown, followed by the number of oxygens. And the one that you see used most often probably are the 15 crown 5 and 18 crown 6. What's really cool about these molecules is that the way they fold due to the bond angles is it creates a situation where on the inside, which is where all the lone pairs are, there's a lot of partial negative. So this basically automatically aligns all these partial negatives facing the inside of this hole. And depending on how big it is and the distance that those lone pairs are from one another, that creates just enough space for a metal atom to fit in there and form an ion, a number of ion dipole attractions that are actually really nice. So if the fit is right, you can fit a metal atom right inside that crown ether. And so here's a space-filled model that shows the size of the metal atom and the size of the ether, and the red are all the oxygens. You can see they're all facing in there, surrounding the metal atom really nicely. And so the 18 crown 6, 18 total atoms in the ring, 6 of them are oxygens, happens to fit the potassium ion just right. And why would I want to do that? We'll talk about that in a minute. Sometimes you want to do a reaction in organic chemistry, and a lot of your compounds are low in polarity. And so let's come back there. Let's imagine this reaction, this reaction here. Right, I've got this low polarity molecule. It's got a leaving group. My goal here is I want to introduce a fluoride ion to come in as a nucleophile in an SN2 and push out that leaving group and put a fluorine there instead. Right? So maybe I want to run that reaction for whatever reason. Without the 18 crown 6, that'd be very difficult to do because this is a very low polarity molecule. And the fluoride ion is highly charged. It's got a negative and it's a very small atom. And so that negative is very condensed. So that negative would have to start off with a counterion, which would be a potassium in this case, Kf. And the fluorine and potassium with their full charges are going to line up and form a solid. And that chunk of solid is going to be very difficult to dissolve, right? How do I dissolve an ionic compound? Normally I would use water, some polar solvent, because the polar solvent can form ion dipole attractions here that keep the ions separate. But if I use a polar solvent, it'll just form a separate layer from this nonpolar liquid, right? So I need a nonpolar or low polarity solvent like benzene to dissolve this low polarity reactant. But if the polarity is too low, then I can't keep the fully charged ions separated and they'll just come together in a solid. So this is a classic example in organic chemistry where you have a problem. You have two reactants you want to combine and collide and be in the same solution, but they're very different polarities, so they don't readily mix. So the 18 crown 6 solves that issue. The 18 crown 6 has, as we showed, the low polarity parts on the outside of the structure. Right, this is my low polarity part here on the outside of the structure. And all the partial negative is on the inside. So this molecule can dissolve in a low polarity solvent because the low polarity solvent surrounds the outside. And so the idea here is by complexing or forming ion dipole attractions between the large partial negatives of the oxygens and the formal positive of the potassium, and then keeping that inside of this molecule that's surrounded by a low polarity exterior, that whole thing can then readily dissolve in a low polarity solvent. And so if I need to dissolve a polar substance in a low polarity solvent, a crown ether is usually an awesome way to do that. So I would start the process off by getting my fluoride ions dissolved in benzene. Benzene is my solvent. It's a low polarity solvent. I need this solvent, as we said, specifically because my other reactant is so nonpolar. There's a tiny electronegativity difference here. It's going to create some small partial charges, but the rest of the structure is pretty much nonpolar. So any polar solvent wouldn't surround it. The polar solvent will just attract the other molecules of the polar solvent and push this into a separate layer. It would form a separate layer, so it wouldn't mix. So the idea here is I need my charged fluoride to mix with my low polarity substrate. And so the crown ether serves its purpose to make that happen, right? So as we were saying, the fully charged ions have trouble separating. But if I mix this up and stir it around real good, the potassium will actually start to be pulled inside of the crown ether to form attractions with the large partial negatives on the oxygens facing the interior of the crown ether cyclic structure. And when the potassium goes inside there, it gets kind of trapped. And that means the fluoride now is free in solution. Normally, fluoride is a terrible nucleophile. We said that last semester because the fluoride ion is so small, any solvent like water that's polar enough to form attractions with it are going to form such strong attractions, it's going to be surrounded by the solvent in a way where it can't get free and effectively attract. It can't get free and effectively collide here, right? If it's surrounded by solvent, the collision is hindered by the solvent getting in the way. So this crown ether serves really two purposes here. It attracts to the potassium, and it allows the fluoride to be free, and it allows all of this to take place in a low polarity solvent. So the fluoride won't be sequestered and protected and hindered from attacking by a polar solvent that forms really strong hydrogen bond or ion dipole attractions to it. Instead, the fluoride would be surrounded by benzene. And benzene at best can form London forces by kind of shifting the electrons around a little bit to create a slight negative end and a slight positive end, and then some minor attractions. So the attractions there are quite weak, and they'll just be constantly breaking, which mostly leaves the fluoride free in solution, so that when I later add the substrate, the fluoride will be able to quickly attack and push that out, and I can get a much higher yield. Normally, you can't do this reaction. Without that 18 crown 6, the potassium fluoride will just not dissolve in benzene. If you use a more polar solvent that dissolves it, it'll be so well solvated by the solvent, it still won't be a good nucleophile. And the other substrate so low in polarity, it wouldn't dissolve in a more polar solvent. So 18 crown 6 does a great job of kind of bringing everything together, pulling the potassium in so the fluoride is free, and then allowing everything to dissolve in a low polarity solvent because the exterior of the 18 crown 6 is low in polarity as well, and it will easily dissolve and stay in solution. If you want to sequester a lithium ion or a sodium ion, since they're smaller than potassium, you just need a smaller sized crown ether. So if you had sodium fluoride on hand instead of potassium, you would add the 15 crown 5, because that would surround the sodium, and then it would have a low polarity exterior. It would dissolve in a low polarity solvent and allow the fluoride to be free as a nucleophile in solution. And so that's just one example. It's very common to sequester these ions with crown ethers. All right, so we've looked at some properties of some ethers and focused in on the crown ethers as an interesting example. And so the next section we want to discuss has to do with how to make ethers. And we had a lab last semester where y'all were asked to make a specific ether. If you don't recall, its structure was like this. We did that one. What a lot of people did was they tried to set up this with a leaving group, and then tried to have the oxygen attack there and push out the leaving group. So there's really a couple different ways to make ethers, and that depends on what leaving group you have and whether or not you deprotonate this alcohol before it attacks. And so we're going to see two examples. So the first one is going to be under acidic conditions. In this case, it's an acid catalyst because the acid is regenerated at the end. So this synthesis for an ether worked well to form symmetrical ethers. So what do we mean by that? What we mean by symmetrical is the R groups on either side of the oxygen are the same. And so if you want to make an ether where both R groups are the same, this is a perfectly reasonable method. It involves taking an alcohol, so whatever that R group is, 2 carbons, I'm going to make a 2-carbon alcohol. And I'm going to treat that with an acid catalyst. And that would promote this mechanism. So what will happen is the oxygen will pick up a proton. It's a weak base, but as long as my acid is strong enough, it will at least create an equilibrium where some of the alcohol molecules pick up a proton. And now I've got a great leaving group. So what's going to happen next? I don't expect the leaving group to leave first because that would produce a primary carbocation, which would be too unstable. So that would require, if this were tertiary or even secondary, that might happen, and then the carbocation would form, and then this other molecule of the same alcohol could attack the carbocation. But in this case, we're not going to form a primary carbocation, so avoid those in your mechanisms. So now that I've got a good leaving group and it's not too sterically hindered, another molecule of the same alcohol, because we just have that sample around, there's lots of those molecules around, would attack and push out the leaving group, and that forms a protonated ether. And so one more molecule of the alcohol would deprotonate. And this, upon picking up that proton, would also produce another equivalent of H3O+. So it's not exactly H3O+, but it serves the same purpose. It has a proton it could donate to another ethanol molecule, and that could keep occurring over and over and over again. And so that's why it's catalyzed, because the acid is regenerated here in the last step. But that forms an ether. It's called a dehydration. And that's because of the net reaction. So let's look at the net overall reaction. Net overall, you're converting 2 of these into the ether. In order to do that, you're losing 2 hydrogens and an oxygen. That's an equivalent of a water molecule, right? So if I take this oxygen and then just take this one oxygen and connect it to both R groups, I make the ether. So in the process of making the ether, you're losing a water molecule, or the equivalent of a water molecule. And that occurs here, right? It's a water leaving group. That leaving group leaves, and that's a byproduct of the reaction. So when it's balanced, it's really 2 moles of the alcohol producing an ether and a water. And so I've got 2 total moles in the beginning, 2 total moles in the end. So here's another example where the entropy change is pretty minimal, pretty close to 0, because there's no net change in the number of moles of reactants. And this is an equilibrium. It can go back and forth. So how do I shift it to the product side? Well, I use excess of the alcohol. The more of that I have, the more by Le-Chatelier's principle should shift to the product side versus back to the reactant side. And I don't put any extra water in, or maybe I try to boil the water out as it forms if possible. If I can remove that, that would help continue to shift the reaction toward the product side. So this is a great method. The problem with it, though, is I can only use it to make an ether when both R groups on either side of the oxygen are identical. If one R group is different from the other, which would be asymmetrical, that's not going to work. So we need an alternative for those situations. And our alternative is what some students used last semester instead of the method we just talked about. And that is to start with an alcohol that's relatively stable and unreactive and add an especially strong base. Right, the hydride NaH is a very strong base, right? It's a very large charge imbalance here. 2 electrons to 1 proton. I've got twice as much negative as I have positive, so it's very imbalanced. So that hydrogen is a strong base. It's going to depronate an alcohol to make hydrogen gas, right? One hydrogen sharing electrons with another hydrogen. That's going to bubble out hydrogen gas as the reaction occurs, helping drive it toward the product side. So this first step is going to be pretty much irreversible. If we look at the pKa of H2 versus the pKa of the alcohol, it's a very big difference there. So that side's pretty much shifting completely to the product side. So I can depronate any alcohol with a hydride. Once the alcohol is deprotonated, it makes a great nucleophile or base. It's got a full negative. It could pick up a proton if I had any kind of protic source around, or if there's an electrophile with a leaving group and it's not too sterically hindered, that oxygen could come in there and push out the leaving group. And so this is the reaction that some students did and had a lot of success with it, with that last reaction, or last semester, where they started with this OH. They added sodium hydride in one step to depronate that. And then I think they added ethyl bromide or bromoethane so that that oxygen would attack there and push out the bromine and install 2 carbons off of that oxygen. So this will work well. There is a limitation though. Once you make your nucleophile, it won't be able to attack if it's too sterically hindered. So this worked well on a methyl group. It also would work on an ethyl group. So if this carbon here is a methyl or a primary carbon, it'll work. That's okay. If it's a secondary or tertiary molecule that you expect that to attack, you're not going to get the product. You're going to get an elimination side product. So let's mention that real quick. Actually, I think that's described on the next slide. Did I miss anything here? Oh yeah, what happens to the halide? Well, it usually be removed. Oops. What happens to the halide? It usually comes together with the sodium to form a salt, which precipitates, or it can be removed by liquid-liquid extraction. So the alkoxide that forms in step 1 is also a strong base, and so that means there are eliminations products that are likely for secondary and tertiary alkyl halides. So the methyl and primary, those are going to undergo substitution. And that's what we want here, right? We want the nucleophile to attack, push out the leaving group to make a new oxygen carbon bond in a substitution reaction. If I have a secondary leaving group or a tertiary leaving group, then it's too crowded. It's too much steric hindrance, especially if this R group is big. Too much steric hindrance for that to come all the way in there and push the leaving group out and do a substitution for the leaving group. Instead, it would be more likely to pick off a beta hydrogen and do an elimination. And so that's major limitation of this reaction. Over here, it would pick off a proton, push the leaving group out through an elimination reaction. And that would defeat the purpose, because we could just buy a base to do elimination. We don't have to make it this way, although that's also a fine way to make a base if you don't have it and you want to start from the alcohol. If you want to make an ether, though, rather than an alkene, you can't do substitution, or you can't do elimination, you need substitution. And that will only work if the oxygen is attacking a methyl or primary carbon. All right, let's see if we can use this approach to make terbutyl methyl ether. Right, so there's, if I want to make an ether, I can start with the oxygen. It should be butyl methyl ether alphabetically. Anyway, if I want to make an ether, I can start with the oxygen bonded to either of those two carbons, and I can form the bond with the other one. Right. So if I start with the oxygen bonded here, it would have to be negatively charged, and I could use this extra carbon here and connect to that a leaving group. Or I could consider keeping the oxygen connected to this carbon the whole time. And having it attack the other carbon. And so now hopefully you're seeing why one of these strategies will work and the other will not. If I use a tertiary substrate with a strong negative charge on an oxygen, it's going to do elimination. That would produce an alkene. If it's not too sterically hindered, though, it can come right in there and push out the leaving group and make an ether. So this is just another example to illustrate how important that is. If you plan a synthesis, you got to think about the mechanism. You got to think about the sterics, and then often there's all kinds of other things to think about, like resonance and all that other good stuff. But in this case, the sterics is really important. So make sure if you plan to do the Williamson ether synthesis and you're able to make a negatively charged oxygen, maybe by starting with an alcohol and using sodium hydride to deprotonate the proton there, so the electrons stay behind and make that negative. You can't have it attack unless it's a methyl or primary site, in which case it wouldn't be too sterically hindered to be able to come in there and push the leaving group out and make the product. So that synthesis won't work. We have to disconnect on the other side, starting with this alcohol and adding this substrate. We can get the oxygen to attack without too much steric hindrance. All right, let's take a look at this one. It's one of my options here. So basically what we learned in the last example is I don't want the oxygen to form a bond with a carbon if it's too sterically hindered. So I don't want to disconnect here. I don't want to have the oxygen start with the ethyl group and then try to attack the ring with some leaving group, because it's too sterically hindered. Instead, it'll probably just end up going for the beta hydrogen and doing elimination, which is not what I'm trying to do here. I'm trying to make an ether. So I don't want to do that. I want to leave that side intact and disconnect retrosynthetically from the other side. Meaning this is the bond I'm going to form because I'm forming it between an oxygen and a primary carbon, which won't be too sterically hindered to do. So working backwards, to make that ether, I would start with the oxygen already connected to the ring. And I would have it collide with some kind of 2-carbon chain with a leaving group, like a bromine or an iodine. That would attack, push that out, and that would give me the product. So then I would just have to determine how to make that, and we just said if you want to make an alkoxide, you can make it from the alcohol, and lots of simple alcohols like cyclohexanol and many other alcohols are available commercially. You just add sodium hydride. You could also add sodium metal. We showed that in the alcohol chapter. If you want to deprotonate an alcohol, you can do that with a strong hydride base, or you could also do it with sodium metal or potassium metal or something like that that goes through a free radical mechanism that we showed last time. But that would pick off the proton, and the electrons would stay behind here to make that negative. So if you have an ether that's got two different R groups. You definitely want the less sterically hindered R group to be the one that the oxygen attacks to avoid the elimination side product. All right, a couple other ways to make an ether. Here's a reaction we saw last semester to make an alcohol. Last semester we said, if you want to do a Markovnikov hydration, specifically, which is an addition across a pi bond, where you're adding hydrogen and OH across the pi bond, right? We're adding OH here, adding hydrogen here. If it's Markovnikov, then the hydrogen is going to end up adding to the carbon that already had more hydrogens. And the other group, which will be an OH, if it's a hydration, is going to add to the carbon that had more R groups. Why does that occur? Well, we talked about how the full mechanism here is very complicated, and we're not going to get into it. But the first part of the mechanism we did mention last semester, and we said what happens here is the mercury attacks the pi bond first as the pi bond is coming out to connect to it. And that forms a three-membered ring with the mercury. So let's just take a look at that three-membered ring real quick. The mercury there, we have a positive. Let's call these 1, 2, and 3. Keep track of where they are spatially. So R1, we could show that going behind. If the mercury came down on top of the pi bond, R1 would be pointing away from me. R2 would be pointing out at me. R3 is on the same side as R2, so they would remain spatially on the same side. Once the three-membered ring with the positive mercury forms, the water is right there, right? They're both added in the same step. And so this positive charge will start to attract the electrons away from the carbon that's sharing electrons with. Which carbon will electrons be pulled away from more? Well, the carbon that can stabilize the positive that results from electrons being pulled away from it more effectively. And that's going to be the one that's more substituted with carbon groups, right? So if I imagine these electrons starting to swing out to the mercury, it would start to look like this. This bond will start to break. This bond won't break as much because if electrons get pulled away here and I start to create a partial positive, there's only one R group to donate electrons through hyperconjugation and induction to help stabilize it. Here, there's more hyperconjugation and induction to help stabilize the partial positive that forms. The mercury is not fully moving away. That would form a carbocation and a broken noble gas configuration on that carbon. That would be really unstable. So the mercury is still sharing somewhat. It's kind of like a partial bond. By pulling away somewhat, it allows the R groups to kind of shift up and occupy some of that space that's now available as the mercury pulls electrons away. But it still has enough electron density in there to block out a nucleophile from attacking on the same side. So the nucleophile, which is water, because that's what we put in there with it, has to attack from the bottom and open that ring up. And so that means the OH, or the water, that attacks there it's going to put this R group, the solid wedge, and this one here with the dash wedge. As that opens up, the mercury is going to end up anti to the OH group. So this is an anti-addition. Why is it an anti-addition? Because the nucleophile is attacking from the back side of where the mercury is leaving on that three-membered ring. It has to, because the mercury is still blocking the front side. Another water would come along and deprotonate this. I would give an OH there. And then the second set of conditions simply replaces that mercury with a hydrogen. So in essence, the reason that it's a Markovnikov addition is because the nucleophile is attracted into the carbon that had more carbons, because that stabilizes and forms a greater partial positive to attract the nucleophile in. And it's also an anti-addition because the attacking nucleophile and the hydrogen add on opposite sides, spatially facing 180 degrees away from one another, or anti with respect to one another spatially. So this is all review. We talked about all this last semester. This is a great way to avoid a carbocation rearrangement because we're not ever forming a carbocation. It's a great way to control the spatial positioning of the nucleophile attacking. We can control the regiochemical outcome where we get the OH on the carbon we want, the hydrogen on the other carbon. And since this works so well, there are other versions of it. If we want to make an ether instead of an alcohol product, all we need to do is substitute the water in this reaction for an alcohol. It's going to be the same exact process. It's going to be a Markovnikov addition. It's going to be an anti-addition across the pi bond. The only difference is, instead of water attacking, it's the alcohol. If I add ROH, any kind of alcohol here, the alcohol will attack. That'll be an R group, ROH. The H will be picked off, and I'll end up with an OR here. And I've effectively made an ether, right? Because the oxygen has one R group on one side and another R group on the other side. So this is a good way to make an ether. You can control the regiochemical outcome and the stereochemical outcome. All right, so that gives us now all the information we should need to answer the second quiz question. Filling in some blanks here, working forward, working backward from what we already have. So we know these conditions are a little different from those ones we just saw. These do an anti-Markovnikov. Anti-Markovnikov is not the same as anti-addition. This is going to be syn addition, but anti-Markovnikov, right? So what that means is I could really think about this forming, because these are hydration conditions. I have to remember the hydroboration reaction adds boron and hydrogen across a double bond, and then the boron gets replaced with an OH. So where was the double bond? Was it here, or was it on the other side? Well, if I start with this alkene, and I do an anti-Markovnikov hydration, that would mean I was adding, the hydrogen would add here, and the OH would add here. That would give me a different product. So that must not be the correct alkene. If I start with this alkene, since there's already a hydrogen here, anti-Markovnikov hydration conditions, which is what we're using here, would cause a new hydrogen, the OH, anti-Markovnikov, the OH would go to there, and the hydrogen would go to here, and that would give us the product. So that must be the correct alkene. If we know the alkene's going to undergo anti-Markovnikov hydration to produce this alcohol, this has to be what the alkene would have looked like. Once I have the alcohol, if I use a strong oxidizing agent we saw last time, that will convert the alcohol into a carbonyl. The oxygen will bond to the chromium. Something will pick off this proton. That will swing electrons in, and then the oxygen electrons it was sharing with chromium will go to the chromium. And that will form a double bond. So the full mechanism is more detailed than we have time to get into, but that's the gist of what's happening there. So now I have difficult situation. I have to figure out how to get from this compound down here in 2 steps. So first thing I'm noticing here is these first couple steps I didn't have any change in the carbon skeleton, but here I do. So I'm starting with 5 carbons, and those are the same 5 carbons. So I have to add a 2 carbon group here and a 3 carbon group here. So first thing I would notice is these 2 carbons are going to come into carbon 2. And that used to be a carbonyl carbon. It used to be a CO double bond. So anytime I have a CO double bond now that I know both LAH and the Grignard reaction, is that this is a great electrophilic site. It's a nice big partial positive here. Draw that again. So because these electrons are pulled away, I've got a very big partial positive at that carbon. And since oxygen, there's another resonance contributor where the electrons shift up, that can really allow new electrons to come in. And so if I want 2 more carbons to come in there, I would add those 2 carbons, and I would connect it to a Grignard. That would allow the magnesium to give those electrons to the carbon, and the carbon would use them to attack and push those electrons up. So when that occurs, now I've got those 2 new carbons attached there. And the oxygen now is negatively charged. All right, so let me just count the carbons again. 1, 2, 3, 4, 5. We'll call this 6 and 7. So we have 1, 2, 3, 4, 5. And now 6 is connected to 2 because 6 is nucleophilic and it attacked the electrophilic site, carbon 2. So normally after the Grignard, normally we do that one step and then add water in the next step. The purpose of the water and or H3O plus is to protonate this oxygen and make it an OH. But I don't want to make it an OH. I want it to be an OR. If I did have an OH, I would want to take that proton off to make it look like this so that it could attack the 3 carbon group it needs to form the product there. So I'm not going to do that. I'm just going to skip that step. Once I've got evidence all the Grignard attacks and my molecules look like this, I'm just going to add the 3 more carbons I need, which are 8, 9, and 10. All right, so I'll just number this 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I need to add carbons 8, 9, and 10. I've already got a nucleophile all set up since the Grignard attack to create a negatively charged oxygen. So I would just add 8, 9, and 10 connected to some leaving group, bromine, iodine. And that oxygen would attack there, push that out, and that would add 8, 9, and 10. It's a really good idea to get into the habit of counting your carbons and thinking through the mechanism to make sure everything gives you the products that you're looking for. If in your quiz answer you protonated this and then added a base to then deprotonate it and have it attack, that should also work. It's just extra steps that you don't need, so I would still give you credit for that. All right, so that's the reactions that you need to know that will allow you to produce an ether. And so now we want to talk about some reactions that ethers undergo. So if you have an ether, what conditions will cause it to react? Right? So we said ethers are good solvents because they have low boiling points, they have some polarity to dissolve a variety of things, and they're not very reactive. Right? If your solvent is just meant to get the other molecules to help them collide, you don't want your solvent interfering with the reaction, right? So ethers are aprotic. They don't react readily with bases or nucleophiles. They're not very electrophilic. The main thing that an ether has that makes it even a little bit reactive, even though they're generally unreactive, is the lone pairs on the oxygen. And because the oxygen is so electronegative and it carries such a large partial negative, those lone pairs can pick up mostly protons. So the main way the ethers react is as a base. If you have a strong acid around, the lone pair can pick up a proton from that strong acid. That's nothing too surprising. So what happens when you add an acid? Well, it depends on the acid. If the acid is HBr or HI, then this is what you'll typically see. So here X could be Br or it could be iodide. All right, so here's just an ether. So this would work on most ethers, depending on the R group. Most R groups, though, don't really interfere with this process. So what would happen is the oxygen would pick up a proton from my extremely strong HBr or HI acid. That makes it a good leaving group. So now the I minus or Br minus can attack here and push out that oxygen. That produces an alcohol and an alkyl halide. But the alcohol is still reacted. It still has large partial negatives and it's still able to pick up a proton if there's strong acid around. So assuming there's still some strong acid around, which you might want to use excess to help promote this full process to occur in a controlled way, that partial negative can then pick up another proton. And the Br minus or I minus that's produced can come in there as a nucleophile and push out of water. So I would get the one R group that was initially connected to the oxygen as an alkyl halide, and the other R group that was initially connected to the oxygen as an alkyl halide, and then the oxygen ends up existing in the form of a water molecule. So this is acid-promoted ether cleavage, or breaking apart the ether using acid. It's not acid catalyzed, it's acid promoted. We'll talk about that on the next slide. So let's do one more of these, and I'll show you an example where we won't get the full reaction that we just saw. Right? So we'll start the same way. So let's imagine X is either Br or iodide. The oxygen would come in, pick up a proton, push out the halide conjugate base. Now this is protonated. It makes a great leaving group. So the I minus or Br minus, let's just say it was Br, it could come in, not to the oxygen obviously, the oxygen already has a noble gas configuration, it can't accept more electrons. I could imagine it coming in here, pushing out the oxygen, or I could imagine it coming in here and pushing out the oxygen. In the last example, since we had two identical R groups, it didn't matter. X could have come in here and pushed out the oxygen there, or it could have came in over here and pushed the oxygen out there. Either way, I'd still get the same set of products. So it doesn't necessarily matter which R group is reacted first once the oxygen is protonated. In this case, though, what we see is this is an aryl carbon. It's like a vinyl carbon in that it's not reactive toward SN1 or SN2. There's no way sterically that the bromine could come in here from the back side because the ring is blocking it. So you can't do SN2. And the leaving group can't leave first and leave behind a carbocation because that would be an empty sp2 orbital. This is an sp2 orbital overlapping here, and the electrons are in a pretty compact space held pretty closely to the carbon. So the leaving group can't leave first, the nucleophile can't get in first. There's no way for the nucleophile to attack this carbon. And that's true if it were an aryl or vinyl site when the carbon is sp2. So that can't happen. So the only thing I expect here in this case is that the Br attack this carbon. So this R group, let's take a look at what it could be. So let's just look at two scenarios. Let's say the R group here is primary. Right, so there's two hydrogens And the Br minus, definitely small enough to make it into a primary carbon from the backside and push out this great leaving group. So that would give an OH, so I would produce phenol. And that Br would be now connected to that carbon right here. So I get an alkyl halide and a phenol. What if the R group were more sterically hindered? Maybe it were tertiary. Well, in that case, the Br minus, even though it's very small and not very sterically hindered, it still wouldn't be able to make it in, right? We don't have any evidence of backside attack on a tertiary carbon. It's too crowded. So what would have to happen first is the oxygen would leave. It would pull those electrons with it to balance its charge. So I'd make the phenol. Oops, that wouldn't have any charge, obviously. I'd make the phenol. Once those electrons leave, there'd be a carbocation. Then, now there's obviously plenty of space. It's very electrophilic for the Br minus to come in and attack. And so I would still basically get the same result. I would get an alkyl halide there and a phenol. Just the mechanism is either a difference between an SN2 versus an SN1. As we were just saying, that works effectively with HI and HBr. It doesn't, however, work nearly as well with HCl, and with HF it really doesn't work well at all. And the reason for that is because of solvation. If we compare Cl minus and F minus versus I minus and Br minus, the F minus is very small and highly negative. The chloride is a little bit larger, so the negatives spread out more. It's not quite as much of a charge imbalance. The bromide is even larger, and the iodide is even larger. So the issue here is not sterics. If it were sterics, we would expect the larger atom to not be as reactive because it'd be too bulky and it would get bounced out all the time. But in this case, it's solvation. Whatever the solvent is, it's going to be polar. And it's going to surround these small atoms very easily. I have a concentrated unstable negative. It's going to form very strong attractions with the partial positive end of the solvent. So it's the same issue we saw before. If the nucleophile is too effectively solvated, it can't get rid of this shell of solvent molecules around it and get free to attack as a nucleophile. And so we would see some reaction with chloride because it's not as badly solvated, but not as much as bromide or iodide because they're larger and the solvent doesn't form as strong attractions with them. And even if the solvent is on a few sides, it's so big it probably has an open side where it could still potentially attack the electrophilic site, specifically in this step here or in this step here, depending on how sterically hindered the substrate is. Okay, so what about this one? Oh, here I would expect first thing to happen would be for the oxygen to pick up a proton and become protonated. I would give it a positive charge. Oops. Making it a great leaving group. The Br minus that's produced would probably come in here first, since it's only primary carbon. It's not very sterically hindered versus this one over here, which is secondary. And so it would probably be coming in there first, pushing these electrons out to the oxygen. So that'll give me ethyl bromide or bromoethane. When the oxygen leaves, I get an alcohol. So do I expect it to stop there? I don't, because there'd typically be either excess HBr or at least some HBr that hadn't reacted with the original molecule yet, and it could easily react here by protonating this. So if this oxygen picks up another proton, it would already had one proton. If it picks up another one, it would become a water-leaving group. And then the Br minus that results, in this case, it's a secondary carbon, so it's not too sterically hindered to show it occurring by SN2 backside attack. And that would probably occur for some of the molecules to push out the water. Alternatively, if the leaving group left first, I'd have a secondary carbocation. It's not too unstable to form, and then the bromine would just attack it, so I'd still get the same set of products. And since this is not a chiral center, it doesn't really matter whether I draw the bromine with a solid wedge or a dashed wedge. All right, so the next section is about epoxides. And we've talked about epoxides a little bit last semester and a little bit this semester. And epoxide specifically is a three-membered ring that's also an ether. Right, so we said an ether has an oxygen with two R groups. Well, what if the R groups are part of the same ring? Well, that would make a cyclic ether, or a ring molecule with an ether. And these two especially are quite stable. They don't have much ring strain. They don't have much torsional strain. So they're not really as useful synthetically. These are mostly used as solvents, especially the furan, the tetrahydrofuran. The epoxide, as we've seen, is very useful synthetically. It's kind of in this sweet spot where it's pretty unstable, right, due to the torsional strain of the hydrogens here on adjacent atoms overlapping, creating repulsion, and due to the angle strain there where the electron clouds on the adjacent bonds start to get a little too close and repel. It's pretty unstable. So I can get a variety of different nucleophiles to attack there and open up the ring, whereas the nucleophiles are not going to do the same thing here because it starts much lower in energy. When I said it's in the sweet spot, though, that's because it's unstable enough to react with a variety of nucleophiles, but it's stable enough to be formed and isolated. You can get an NMR on it and verify its structure and make sure that you've correctly synthesized it. So there's a lot of reactions you'll see where people will make an epoxide specifically so that they can attack it with a nucleophile and convert it into something else. And so it's definitely the epoxides that are most stable, or at least stable here, and most reactive due to the ring strain of the three-membered ring. So if you're naming an epoxide, before we get into more reactions that epoxides undergo and can be formed through, if you're naming an epoxide, there's really two naming systems. If you look at the structure of an epoxide, you can see there are up to 4 R groups that could be there. Those could be hydrogens. I could put any one of those in as an R group. The bigger the R groups, the more the ring strain, because the torsional strain is going to be much bigger when you have eclipsing groups that are larger and sterically hindering. Nevertheless, as we said, they are stable enough to exist for a significant period of time, and they are formed in nature, especially commonly in pheromones used by insects. So that's pretty cool. Those structures exist long enough to be produced by insects as a way of communicating. So the two naming systems for epoxides, the main difference is in what is treated as the parent chain. So here is an exception to a rule that we said way back last semester. We said, if you're going to include carbons that are part of a ring as your parent chain, you can only include those carbons and not any other carbons outside of that. This is an exception to that. So the first naming system for epoxides involves finding the longest chain of carbons, 1, 2, 3, 4, 5, that includes the carbons of the epoxide, which is obviously carbon 2 and 3. And then to name the oxygen as a substituent with the word epoxy. Right, so I've got 5 carbon parent chain, that's pentane. I've got epoxy, bridging carbons 2 and 3. So 2,3 epoxy is communicating that we've got this epoxy or 3-membered ring, bridging carbons 2 and 3 with an oxygen. And then obviously I've got a methyl on 2 and an ethyl on 3. So I can name the structure that way. Alternatively, the word oxirane can also be used as the parent chain. If you use this as your parent chain, you can only include the oxygen and the 2 carbons that are bridging it as the parent chain. You have to name everything else as a substituent. And so there are 2 ethyl groups on carbon 1, that's 1,1-diethyl, and 2 methyl groups on carbon 2, 2,2-dimethyl. So either of those would be the correct way to name those rings. The second one is a little tricky because if these R groups get really complex, it might start to be more difficult to name them. And so that's what we see in a couple examples here. So let's say we're naming these epoxides. For me, to name this as an oxirane and then try to name this as a substituent and this as a substituent, that's not going to work. There's no way of doing that. So really what we need to do is to name this as my parent chain, and then the oxygen as a side group, and this as a side group. So the parent chain would be here would be cyclohexane. In this case, you could number 1, 2, 3, 4, 5, 6. Or you could number from this carbon 1, 2, 3, 4, 5, 6. Either numbering would be okay. Either way, you get something on 1, 2, and 3, whichever way you number it. And an oxygen is basically equivalent to an oxygen in my book, so don't worry too much about prioritizing ethers versus epoxides when numbering. So let's just go with the inside numbering here. I've got this group on carbon 1. Carbon 1 has an oxygen with an ethyl, so that's an ethoxy. One ethoxy. And bridging carbons 1 and 2, I've got a 1,2 epoxy. Epoxy means you've got the 3-membered ring, and the 1 and the 2 tell me which carbons. I'm sorry, that's 2, 3. 2 and 3 are the carbons that the epoxy is bridging. And so EP comes before ET alphabetically, so it would be 2, 3, epoxy, 1 ethoxy, cyclohexane. So this one here, I could also use either naming system, but again, since I have kind of a complicated R group down here, it makes more sense to find the longest parent chain that includes the epoxy carbons and make that my parent, and then name the epoxy and the other as substituents. So to do that, I would go 1, 2, 3, 4, 5, 6. So that would be hexane. I've got the ethoxy on 2. I've got an epoxy on 3 and 4. Again, EP comes before ET alphabetically, so it'll be 3, 4, epoxy, 2, ethoxy, hexane. All right, so how do we make an epoxy? Well, we talked about this last semester. We saw the mechanism, although I didn't ask you to memorize it or be prepared to draw it. Hopefully you at least remember how to make an epoxy from an alkene. Talked about this when we talked about alkenes in chapter 9, addition across alkenes. So what happens here is this per acid or peroxy acid has two oxygens and they're unstable when they bond together. The classic peroxy acid that's used to make an epoxide is usually MCPBA. So we see MCPBA, this is its structure. The rest of this structure isn't really that important for the mechanism. It's the CO, the O single bond there that makes that reactant. So really almost any peracid can be used to do this reaction. So basically the pi bond breaks and gets replaced with a couple sigma bonds there to make the three-membered ring. When this occurs, it is stereospecific. That means if two R groups are on the same side of the alkene, they remain on the same side of the ring, either both solid wedges or both dash wedges. There's no way to control which, because it would depend on whether the oxygen adds across the pi bond from the top or from the bottom. But as that three-membered ring is forming, there's no chance for this bond to rotate. So there's no way for the R groups to end up on opposite sides. If they start on opposite sides, there's still no chance for the bond to rotate. And so they end up on opposite sides. One solid, one dashed. And so I'll get the other version of that as well, where maybe this one had the dash wedge and this one had the solid wedge. So make sure you look at the stereochemistry as necessary when dealing with epoxides. Another way to make an epoxide is through the halohydrin reaction. If you recall, the halohydrin reaction is where you have an alkene and you add Br2 in the dark with water specifically as your solvent. So I'm not going to go through the full mechanism, but in essence, the first bromine adds across the pi bond to form a three-membered ring. Normally, the other bromine would attack, and I would add two BRs across there. But with water as the solvent, I expect water to attack. And what's nice about this is the water has to attack from the opposite side from where the bromine is. So if the bromine happens to be blocking the front, the water would have to come in from the other side. And so it ends up anti with respect to the Br once it's deprotonated and converted into an OH. So that gives me an OH and a Br on opposite sides of the ring, which sets it up for a reaction to form an epoxide. All I need is a base here. So what happens there is the base picks off a proton from the alcohol, makes it an alkoxide, and then it can directly attack the neighboring carbon and push out the leaving group. See how it allows that to occur from backside 180 degrees away from where the leaving group leaves. This only works because these two groups are anti 180 degrees with respect to one another. And that's the result of the halohydrin reaction. And so when the oxygen connects there and pushes the bromine out, you get the three-membered ring. So there's a lot of bullet points related to that you should obviously be prepared for when we have our exam on this next week. Fair amount of practice there, not too much. Let me know if you have any questions with that or need help with it. And then next time we're going to continue here with chapter 14, and we're going to look at some reactions that epoxides undergo. And then we're going to talk about some sulfur-containing compounds a little bit. So you want to read up on those sections and check out the videos so that you'll be able to make the most of the lecture and potentially answer the quiz questions, obviously, that are due Wednesday before 1 p.m. Any questions about anything? All right, well, feel free to speak up or type anything if you do have any questions. go ahead, Cody.